So we're going to kind of continue talking about polynomials. We did this a little bit in the previous chapter, basically just defined what a polynomial was and did a little bit of basic vocab stuff. Today we're going to kind of dive in a little bit deeper algebraically. But we're going to start with some vocab. So first piece of vocab we're going to talk about is extrema. When we talk about the extrema for a graph, what are we talking about?
Minimum and maximum.
Yeah, the highest and low points, yep. And if you recall, there's two different types of extrema. There's mins and maxes. And there's two different types of minimums and two different types of maximums. There's local and global. Yep. Exactly right. No problem. The other thing we need to talk about are zeros. What are the zeros for a graph? The x-intercepts, yeah. So let's say we wanted to locate the zeros in the extrema for f of x equals x cubed minus x. So if you type this into your calculator, you might get a graph like this. What are the... Okay, so -1, 0, and 1 are these zeros. Sure. Well, I got some papers up here for you too. You're welcome. Mm-hmm. Okay. So to find the extrema now, what are the extrema? Mm-hmm. But how would we actually find the numeric values for that? Yeah, for sure. Not a question that we can answer algebraically without calculus. And that's not the class that we're in. Although if you came back during first hour, we could, and ask somebody there, they could tell you how to do that. It would probably take them a week to explain you the background. And we've been doing all kinds of funny zooming, so I'm just going to do zoom standard to get my graph. So I know that I have a local maximum here and a local minimum there. So I'm going to use the max command to find the local maximum. I'm going to move my cursor somewhere left of where that maximum is. And then somewhere to the right of where I think that maximum is, and then the guess doesn't matter. So negative 577 and then 385. And then the local minimum, I just would repeat the same process. I'm going to skip the calculator buttoning for that because we've done that already, right?
Yeah.
Hopefully it's not surprising that it's like the same numbers with opposite signs. Looking at the graph, it looks pretty symmetric like that. Okay, so the next thing we're going to point out is that there's a relationship between the degree of our polynomial and the number of extrema that we'll see in the polynomial. What was the degree of this polynomial? 3. How many extrema did we have? 2. What do you suppose the relationship is?
1 less.
Close. It's not exactly 1 less. It's at most 1 less. You could have a situation where you have degree 5 and you have 4, 3, 2, 1, 0 extrema are all possible.
Yeah.
But you can't have more than the degree. And then if we look at the zeros and the degree, how many zeros did we have? 3. And the degree was 3, so we're going to have at most n zeros, like 3 zeros. So you could have a situation where you had 2 zeros, 1 zero, no zeros, all possible for a degree 3 polynomial. But the most you can have is 3. You could never have more than 3 zeros in that specific instance. Let's do a little quickie example here. So for the function f of x equals 3x to the 4th minus 5x cubed plus 2x plus 2. How many zeros could there be and how many extrema could there be? Well, first thing we should do is do the degree. What's the degree here? That's 4. Biggest exponent on our variable. So zeros, we would have at most 4. You could have also written that as like 0, 1, 2, 3, or 4. Would also be okay. You could write that either way. I mean, I like at most 4 because that seems like a lot less writing to me, but it's not incorrect to write it the other way. And then extrema, what would we say for that? At most 3. And again, you could say 0, 1, 2, or 3. Also okay to say it that way. Again, I'll take the at most. Because what if the degree is like 72 or something? Like, I ain't writing all those numbers down. Like, get out of here. I got better things to do with my time. Right? I have wizards to kill or something. Yeah, some magic archers. That's right. Yeah, those are some bad mamas right there. All right. So the next piece of vocab we're going to talk about is something called end behavior. And did we talk about that in first semester? I can't remember.
We did it last year.
And we did it last year. Good. Okay. What is end behavior? Yeah, what is end behavior really describing?
Lost. I don't know.
It describes the arrows on the graph.
Oh, like increasing and decreasing?
Nope.
Nope. Okay.
It describes whether like the arrows at the end of the graph are pointing up or pointing down, or if there's an asymptote in the middle where you have arrows pointing something.
You have to like write that magical stuff on the side.
What? I
Yeah.
know where you're getting at. The magic order. It's like some.
Yeah. What was that called?
It's like if it's positive or negative.
So in this class, we're going to introduce a new notation to describe these. Okay, this new notation is called a limit notation. You remember that?
I said I don't. It's
Okay.
like the negative.
So let's say that we're looking at a graph. And it looks like this. Let's say the name for that graph is f of x. Everybody's okay? So this graph has two arrows on them. Everybody agree? Actually, I'm going to color code these. I'll circle one of them in blue. So if I were just describing what these two arrows are, the one in red, I would say that is is it left or right?
Left.
Left arrow. And is that arrow pointing up or down?
Down.
Down. Okay. So to translate that to limit notation, we write the limit, Lim, and then to write left end, we'll write x approaches negative infinity. So this just means kind of left. Okay, that's the part that you need to do. And then we need the name of our function. In that case, it was f of x. Then equals. And then, because it's pointing down, we'd say negative infinity. This is the way I like to present this, as we're just translating what we're seeing with our eyes into a new set of symbols. That's all we're saying, okay? So we don't need to make it more complicated than that. We'll kind of build out this idea and add on some of the layers of complication. But an end behavior is really intuitive. If I can look at a picture, should be able to tell you what the ends are doing with my mouth, just using normal vocabulary words. Translating into symbols then, let's just take our normal vocabulary and layer the symbols on top of it. It feels like the easiest way to approach this. Now let's look at the blue. What would you say is going on there?
Right arrow.
Okay. So to describe the right part, we'll write limit x approaches positive infinity. And I'm going to write the plus sign down there. You don't have to put it there. I always do, to make sure that I'm just in the habit of writing either a positive or negative there. So I don't forget to write the negatives on the negative ones. So again, that part is just the part for my right. And then we write f of x equals. And then what do you think we're going to write for up? Positive infinity. You got it. Okay. So going from a graph to a end behavior description using a limit is pretty easy, right? Could you do the same thing using a table of values? Let's do this. Actually. So let's say that we have this function, and we want to describe this using a limit. So you could graph and look at the picture. But you could also look at a table of values. If I look at the x values, what's happening here? Oh boy, that was They're just getting bigger, right? So I could write the limit as x approaches in positive infinity, because what direction is my x going? To the right. Exactly. And then if I look at the y's, they're also increasing. So this is going to go to positive infinity. Maybe I could write. Well, you should do it for both ends of your graph. Right? So then I could also then look up in a table my negative values. And likewise, I notice that these guys are just getting smaller. And these guys, again, are getting smaller. You notice the negative number is becoming bigger. So we could write it the same way, just with negative infinities. Yeah, you got it. Now, what's the likely question? How do I get that table out of my calculator? Right? Well, the easiest way to do this is we're just going to go in and type in our function into that y equals menu, just like we've done a bunch of times before. Once I've typed that function in, I'm going to exit back to the main screen, and I'm going to retrieve the y1 command, just like we did in the previous chapter. Where do I go to get the y1? Vars. Then what? Yvars, great. Function. Quick y1. And then I can just do y1 of, like 100. Press enter, there's my number. If I press second and enter, it'll give me the last thing I typed in. I can just go back and edit that to make it 1,000. Press enter. If I press second and enter, it'll give me that same thing I just typed in. I can just go back, edit it, add another 0. Boy, that was really quick, right?
Yeah.
To get 3 values. That's I think, the easiest way to generate the things in your table. And I would say that like 3 values like that are fine. And there's nothing magic about 100, 1,000, and 10,000. They're just like getting arbitrarily big.
Yeah.
You could have picked 16, 2,048, and then 10,892. Like, that would be fine. I don't know why you would do that. Those are weird numbers to choose, but that's fine. They're just getting like an order of magnitude bigger each time. And then obviously you could do the same thing with the negatives, right? Like, no big deal. Does that feel okay?
We could still just have like we just use the
Yeah, it depends on what the directions would be. The directions might say like justify your answer with a table or something, and if that case, it's just, doing that. What do you guys think? That's section 1. That's not bad at all, right? Just a little bit of vocab, doing a little bit of calculator stuff. The nice part is all the commands we're using on our calculator are already things that we've done, which I love. All right. So the next section we're going to be talking about is finding the zeros for polynomial functions. Yeah, and we're going to be emphasizing this algebraically rather than graphically. Exactly right. So let's say we want to do this. Sometimes this can be really easy. Sometimes it could be a bit more challenging. So if I want to find the zeros for any function, what am I going to be replacing the f of x with? 0. Because if the zeros for my function are the x-intercepts, what is the y-coordinate for an x-intercept? Always 0. Okay. So we're going to be solving this polynomial. Go back to your Algebra 2 class for a moment. How do I solve a polynomial that looks like this? First thing you'd want to look for is a greatest common factor. Yes, very good. Do you see anything in common between all three terms? An x, right? I heard somebody whisper it. That's right. So if we factor an x out, it's going to look like that. Now, if we look at this, that should be something you recognize.
It's, what do you call it? Something, what do they call it?
That's a quadratic. But there's a typo here. Yeah, this should be +8. Excuse me. Yep, good. So how do I factor a quadratic like that?
You start off.
I wrote it down wrong. Yep. Which part do you start with? The multiplication question first or the addition question first?
Multiplication, because PEMDAS.
Also start, yep, we want to start with the multiplication. So what are things that multiply to give us +8?
2, 4,
2 and 4?
1 and 8.
1 and 8. You're missing some.
0,
How about -2 and -4, -1 and -8? Okay, so those were our 4 sets of numbers. Which of those are going to add up then to give us -6?
-2, -2. Oh yeah, I forgot to do that. I got into like that extra smart. And I was like, I didn't know what number it came with. It was like x minus 1 squared.
I mean, just do it on your calculator, homie.
Yeah.
How do you do it on your phone?
You just graph it and find the x-intercepts
How do you do that?
with the intersect command.
No. Why?
Type it into-
Trace, second, trace, or trace. And it gives you all of the factors.
Well, to give you the intersect command.
One equation.
Okay, once you've done this, then what do we do? Because we haven't solved anything yet, we just have this factored now.
Now we, I want to send that next thing.
What we do is we apply the zero product property. So if you have two things that multiply to give you 0, what can you say about those things? At least one of them has to be 0, right? The only way to get 0 through multiplication is if something is 0, right?
Yep.
So we can do the same thing here. We can take each of those factors, set it equal to 0, and solve independently. So x equals 0, that's already solved for me. Add 2 over to both sides, and add 4 over to both sides. And those are my 3 zeros for the function. X equals 0, x equals 2, and x equals 4.
Awesome.
Good, yeah. At most.
It could be like this.
They're not always going to be true.
They're not always going to be equal to 0. What is they?
These little equations. X equals 0, x minus 2.
Yeah,
That's how you find it.
They are always.
you can only do this when it is equal to 0.
Okay. Gotcha. You have to set this in 0.
Now you-
Okay.
right? That was our first step, was taking f of x and making it 0. Let's do another, right?
Where's your calculator?
Okay.
That's a whole ice period and then 6 ice period.
So this one asks to find the zeros and the multiplicity of the zeros for the function. We'll talk about what multiplicity means in a second, but before we can do that, we have to find the actual zeros. So we start by setting it to 0.
What?
Okay. Now what?
Let me back it up.
Take the greatest common factor of x. Very good. Then what?
Go find your GCF or whatever, greatest common factor.
Oh, we already did that. That was the x, right?
There's the other stuff where you gotta find like 1, 8, the multiples.
Want to find the things that multiply to give us 9,
Is that our multiples?
and then add to give us 6.
Yep.
What are the things that multiply to give us 9?
1, 9, 3, 3, negative 1, negative 9, negative
Okay. Which one of those add to give us 6?
3, 3. Yeah, all the and all.
Everybody's good with that? I take each factor and set it equal to 0. And then we can solve them each independently. Okay, how many solutions did I get here?
3
Look closely.
or 2. But
2,
1.
right? My solutions are x equals 0. This has a multiplicity 1. And what is my other solution is x equals negative 3. That has a multiplicity of 2. Because it occurs how many times as a solution?
That's what it means.
Twice. That's all multiplicity means. It's just the number of times you get that number as a solution. That's all we mean by multiplicity. Now, here's a case where, how many solutions did we get?
3,
2. What was the degree though? 3. Where did that extra solution go? Well, it was a multiplicity. I just got the same answer. I kind of got 3 answers, but not really, right?
It just means how many times you get that.
How do you know how many times you got?
Look, you got x equals negative 3, x equals negative 3.
So you got, yeah.
Now, the next thing we'd want to ask, is there a relationship between the graph of our function and the presence of a multiplicity? I wouldn't be asking this question if there weren't, right? Definitely would be. Okay. So here's the deal. Let me finish this idea and then we're leaving for lunch, okay? Just a quick little idea. So here are 3 different x-intercepts. If our graph passes straight through that x-intercept of whatever, 0.4, that is a multiplicity of 1. If we have a x-intercept that hits the x-axis and then goes back the same direction it goes, that's called a bounce. And the multiplicity isn't 2, but it's an even number greater than or equal to 2. So that could be used 2 times, 4 times, 6 times, 8 times, 27 times? No, but 28 times maybe. And then if there's one like this where it's like half of the parabola and then the opposite side of the parabola, but it's each on either side of the x-axis, this is called a bend. And it's not multiplicity 3, it's multiplicity that's odd, greater than or equal to 3. So 3 times, 5 times, 7 times, 12 times? No, but 13 times, maybe. Okay, we'll stop here and then come back more after lunch. To this point, we've looked at examples that have been purely algebraic. So let's take a look at an example that's a little bit more like real world-ish. Oh, excuse me. So here it says a company wants to create a cardboard box with an open top. So like a garbage can kind of shape where it's rectangular. The box needs to have 500 cubic inches of volume and is created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. That's what we've got here. So the shaded parts would be the parts that are gone, and you fold up the tabs along the perforated edge here and you get a box, right, with no top to it. The piece of cardboard is 26 by 20. What size square should be cut from each corner in order to create the proper volume?
You don't know my life story. You can't say.
So, next up,
I think you need
all right, so let's think about what we know here. We're told the box needs to have a volume of 500 cubic inches, right? How do I calculate the volume for a box?
Actually, no, that was also on the ECT. Based on length
V equals length times width times height.
Yeah.
He can tell us he's the smartest person in the world. That equation was given to you.
on the ECT.
Yes, they did.
You took the writing.
I had all the same.
All right. So let's go by. Stop talking, please. Let's go and label now the length, width, and height on our picture here. So that I'm going to call the length. This side I'll call the width. And that side I'm going to call height. Actually, we should say that's not really the width. This is the width. Everybody cool with that? Okay. So it says then the piece of cardboard is 26 inches by 20 inches. So I'll go ahead and label that. And what is this question asking for? So I'm going to call that distance x. Everybody okay with that? So my goal now is going to be to take my equation for volume and rewrite it. So instead of being in terms of length, width, and height, It's just in terms of x's. Okay? So how can I rewrite length in terms of x's? I know the length is equal to 26, right? So this distance would be L plus x plus x. Or that L is equal to 26 minus 2x. What can we say about the width? Okay. And how do I get that 20 side? X plus W plus X is equal to 20. And then what's the height got to equal? What's that height got to be in terms of x? Those shaded parts are squares. So h is x. That's it. Just x. Yeah, it's one of the side lengths of the square, isn't it?
Yes.
That's it. So if we put this all together now, volume is length times width times height. We'd say 500, that's the volume, is equal to the length, 26 minus 2x, times the width, 20 minus 2x, times the height, x. So far, so good? Okay. I'm going to FOIL that part out. When I do that, I get 4x squared minus 92x plus 520. And then when I distribute the x through, and then I'm going to get the thing equal to 0. Now, how do we want to solve this? Notice there's no variable greatest common factor. Probably could divide by 4. I'm not sure that 92 is divisible by 4, but I'm sure everything else is. It is. Okay. We can do that if you'd like. Sure. 92 divided by 4, what's that? 46, and then 23, yep. And that's going to be 2, yeah. I was going to get there. Mental math's hard, guys. 125. What's up?
Don't we put a parenthesis in 4?
Well, I divided.
Oh, okay.
I mean, you could factor it,
Yeah.
but if it's a constant, I could just divide. If there's two sides of the equation where it's equal to 0, I can just divide it over, and it's gonzos. But what I'm left with is really no easier to factor than what I had before, right? What do you suppose I'm going to do? If you're ever unsure on how to solve something, yeah, so this is what I had mentioned to you earlier. So we can just type this into our calculator. And what are we going to be looking for when we graph this? The x-intercepts, Yeah, the zeros. Now I'm going to set my window here a little bit intelligently. So in this case, what can the x is representing the side length of one of these squares, right? What could be the smallest value that square or the side length for a square can have? 0, right? Okay. And what would be the biggest length that could be in this context? Not 500. Less than 20. 10. Why 10? Yeah, if this was 10 and this was 10, it would be the whole width, right? So that's good there. The y is the volume. Sure, 0 to 500 seems okay to me. Will probably be more than we need, but that's fine. I don't mind. Okay. There's my graph. What am I interested in? You may. Those values right here, correct? So to find those, I'll press second and trace. Select the intersect command. Oh, not the intersect command, Mr. Kulik. I want the 0 command. Silly Billy. So left bound, I'm going to find this x-intercept first. So I'm going to move my cursor until I see the y-coordinate go negative, because I know that before that x-intercept, it's below the x-axis. That should be fine. I'll press enter. Scroll till I see it go positive. That looks good. Press enter. Guess. So
we don't want it to be negative?
So it's asking us to find a point in between, like one point to the left of it, one point to the right of it. So I picked, on the left, I noticed the y-coordinate needed to be negative because my graph was below the x-axis over there. And to the right of it, my y-coordinate would be positive. So I picked, that's how I was looking at, because I can't really see where my cursor is because the stupid words are at the bottom.
Yeah.
That's what I was using to make sure that I had it.
Oh, okay.
So if you had regraphed it with a better window where you could see where it was like the x-axis was like in the middle of your page instead of at the very bottom,
Yeah.
you wouldn't have to really worry about that. You could just look at where the cursor was.
Oh my God.
Because of where everything was positioned, instead of going back and redoing the window, I was just reading where the cursor was at, the coordinate it was at, and using that as my guide to know when I was on the left side of the x-intercept and when I was on the right side.
Gotcha.
Is that okay?
Yeah, so the y, like, it would be like on my left bound, like y equals 0.56, and that's fine.
Needs to be a negative number
Got it.
because it needs to be below the x-axis and then above the x-axis.
For right.
Well, yes, then the right bound would need to be above the x-axis. So I just needed to make sure that somewhere in between there we crossed.
Gotcha. Now I actually see.
Okay, so I got 1.20. And my other solution was so again, here on the left, my cursor should be above the x-axis. So any y with a positive value would be fine. So that looks okay to me. And then I'm going to keep going. Once I'm on the other side of that x-intercept, my y should have a negative value. So any y with a negative would be a good right bound here. and then guess whatever. And then I got 7.02. That's strange. Oh. No, 520 should be, that's just an error. Okay. Okay. Should we check this? So what can I do to check this?
Y1, sorry.
Yeah, if I do y1 of 1.2 or 7.0, I should be getting what number? Yeah, the 500. Oh, well, not quite 500, right? What am I going to be getting? Ooh, that's weird.
Yeah, I got you.
Weird. Oh, yeah. They should be giving me 0, which is about what we're getting.
Yeah.
What should I here to check it? We're going to do this. We're going to plug in
Wait,
20.
Look, this might be a dumb question, but how'd you get the 92?
The 92?
Yeah, that 92X. Wait, guys, I swear 26.
I just foiled it out.
Is 26 times
26 times 2 plus 2 times
2?
20.
Oh. I'm seeing.
Just foiling.
Gotcha. There's nothing you can do. Because I know these are next.
There we go. So I went back and I typed in this length times width times height. Oops. So there we go.
He's playing like Clash of Clans
Why didn't I get exactly 500? Alexis, why?
The decimal.
Yeah, what decimal points?
Core volume is
The 1.20 is like estimated. It's around.
Yeah. So I'm not going to get exactly 500, but it should be pretty darn close, which is what I did get. Everybody feel okay?
I'm a little confused on the graph. Like, I'll ask you later though.
Well, we're basically at the stopping point.
Oh, we are.
Yeah.
It's like. Oh.
Basically, at a stopping point after tonight, after your quiz.
Mhm.
We have a quiz, and Miss McGinnis says
Okay. So you guys should be able to do up through 15. Up through 15. We're going to stop here. You can spend the rest of the time in class here today working. Okay?
Okay.